to the final lecture of this academic year. My name is Mary Jo Fresh. I'm chair of the steering committee, and I welcome you. And it's my pleasure to introduce our speaker tonight, Dr. Brad Peterson. Brad Peterson was chair of the astronomy department until his retirement in 2015. His primary research interest is quasars, which are supermassive black holes that reside at the centers of large galaxies and are accreting matter at close to their theoretical maximum limit. He received the Ohio State Distinguished Scholar Award in 2010. He is currently a distinguished visiting astronomer at the Space Telescope Science Institute, where he was resident from 2016 to last September. Brad has served on various NASA astrophysics committees for the last 30 years, most recently as chair of the NASA Advisory Council's Science Committee. Last year, he was awarded the NASA Exceptional Service Medal, NASA's highest non-flight recognition. He is currently retiring chair of the astronomy section of the American Association for the Advancement of Science and is also an AAAS fellow. Currently, he is serving as community co-chair for the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, Mission Concept Study, one of 4 major mission studies that have been commissioned by the NASA Astrophysics Division. He is also working on a related study about how to service and assemble extremely large telescopes in space. Today, he will be telling us about LUVOIR in his presentation, a vision for NASA in space astronomy in the 2030s and beyond. Please join me in welcoming Dr. Brad Peterson.
Thank you very much. It's a pleasure to be here. Thank you for inviting me to do this. I have to get this going here. Okay, most of you are familiar with Hubble Space Telescope. You can hardly find a school anywhere in the country that doesn't have pictures of Hubble or pictures taken by Hubble. It just celebrated its 29th birthday in orbit just this last week. Remains a workhorse. In fact, because of surfacing, it's a better telescope now than it was when it was launched. Another observatory is the Chandra X-ray Observatory, which has been operating for nearly 20 years. It was launched in 1999. Another big space telescope is the Spitzer Space Telescope, an infrared telescope that operated at cryogenic temperatures, meaning it was cooled by liquid helium. And when the liquid helium ran out, it could only observe at shorter wavelengths, but it's still doing that, but it's closing out its warm mission. We're going to lose contact with Spitzer is what's going to happen. It's slowly drifting away from the Earth, and we can't get the data rate high enough to obtain new astronomical data anymore. The next one up is the James Webb Space Telescope, which is now scheduled for launch in 2021. Following that is the Wide Field Infrared Space Telescope, known as WFIRST, which is also expected to launch sometime within the next decade. So what these things all have in common is that they are the NASA astrophysics flagships. They are the biggest space telescopes that we have, and we can basically build and launch one of these at a time. It usually takes about a decade or so to implement. And actually, if you look at the numbers here, you see that from the time they're recommended until they're launched usually closes on about 20 years. Characteristics of flagship missions is they do a broad range of science because they have to serve a large user community. They do science that has to be done in space. That's always our single most important criterion for space astronomy. You can't do it from the ground, either because the Earth's atmosphere is opaque at the wavelengths you want to observe, or because you need higher resolution images than you can get through the Earth's atmosphere. Each one of these is a technological challenge. James Webb is especially a good example of that. There were a lot of technologies that simply had to be developed for that mission to happen because it's going to have such a low operating temperature. It's going to operate at 40 Kelvin, 40 degrees above absolute zero, and it's passively cooled. Each one is complex and as capable as the current technology will allow. So the bottom line on this is they're all very expensive. And you can see adjusted to fiscal year 11, the cost of the 4 missions that I've talked about. And W first is undetermined at this point, but it's likely to have more of a Spitzer type price tag than a JWST type price tag. So these are big, important missions. Why do we keep needing bigger telescopes? Why do we argue that we need telescopes that are larger and larger? Even from the time Hubble was launched in 1990, within 2 years, we were starting to have meetings. We were thinking about the next big telescope, the next big optical infrared telescope. Well, there are 2 fundamental reasons. The first is the amount of light that you can collect at a given amount of time goes like the collecting area of your primary mirror, your big mirror. So that goes like its area, so it's proportional to the diameter squared. The other thing, and this is a little bit more subtle, has to do with what we call diffraction. That whenever you have an aperture, there is a limit to how precise an image you can make. And the bigger your telescope is, the smaller the image is that you can make. So this is what a diffraction pattern looks like. If I could look at a star at very, very high resolution through a perfect telescope, this is what it would look like. You see the central image, but beyond that you see a series of rings which are due to diffraction. Diffraction then, it also goes, the size of the image, the diameter of the image goes like the diameter of the telescope, or is inversely proportional. So it depends on the ratio of the wavelengths to the telescope diameter. So the bigger you make the telescope diameter, the smaller the image you can make. And when you're trying to detect very faint things against a background, there's background light due to unresolved stars in our galaxy and unresolved galaxies that are far away, and due to zodiacal light in our own solar system, that is dust particles that reflect the sunlight backwards. Space is dark, but it's not that dark. So when you want to look at the faintest things, you have to see high contrast between, say, stars and that background. So you want the image to be as fine as possible. So the size of the image then is going to go like the square of this. So we have another factor of the diameter squared. Now this shows it very clearly. This is an attempt to look at a star with a ground-based telescope. And this is, by ground-based standards, this is an excellent image. And if you look at the middle panel is what Hubble saw when it first went on orbit, and they found that the mirror was the wrong shape. But with the first servicing mission, they were able to put corrective optics in front of that mirror, because the mirror was perfect, it was just perfectly wrong. And they knew exactly how to compensate for that, really just like eyeglasses. And then you got, with the Wide Field Planetary Camera 2, the image that you see on the right. And this is the same field in each case. So you can actually see some diffraction around this star, and you also see these linear features too. You see these on images of bright stars everywhere. That's diffraction as well, and that's due to the spider that holds the secondary up above the primary mirror. Because the light goes down to the primary mirror, back to a secondary, and then back down through a hole in the primary into the instruments. So that's why you see that. So you can see that if you make the images smaller, if you make them tighter, you can see fainter things against the bright background of space. So you win then on 2 factors. You win on the area, the collecting area, and you win on the diffraction limit. So the power of your telescope goes up like the diameter to the 4th power. So it's very sensitive to that. Okay, so if we want to do big science, we want to use big telescopes. And what we have done, and what we will continue to do, is you make the biggest telescope that you can fit into a launch vehicle. In the era of the space shuttle, that was a 2.4 meter, 100-inch mirror. That was the largest that you could fit in the space shuttle bay. With the James Webb Space Telescope, this is a little different now. This mirror isn't a single monolithic structure. It's 18 hexagons that are folded up on two wings and a main structure, and it will open up when it deploys in space. But this is the largest telescope that you can fit in an Ariane 5, which was the biggest launch vehicle at the time they were making a decision about how to get it up there. So people who design space telescopes refer to this as the tyranny of the fairing. The fairing is the nose cone of the rocket. It's where you put your payload. So that's what limits how big a telescope you could make. Now, there are mass considerations as well. so that you have to worry about. And we'll talk a little bit more about those later. Okay, one of the earlier slides I showed, I mentioned that these are recommended. These missions were all recommended at some point and then launched typically almost 20 years later. So the question is, who's doing this recommending? And the astronomy community has historically done a very good job of setting priorities for the discipline. And the way we do this is every 10 years or so, the National Research Council convenes a decadal survey committee made up of prominent astronomers, and most of the astronomy community participates in one way or another, providing white papers or sitting on committees and pulling everything together. And the decadal committee then lists its priorities for facilities for the next decade. And that goes in two parts, ground-based facilities and space-based facilities. And these flagships were the #1 priority for each of the decadals, starting in 1972 with a recommendation to do the Hubble Space Telescope, and more recently in 2010 to do the Wide Field Infrared Space Telescope. NASA, and I say a fair amount of the community, wasn't particularly happy with the outcome of the last decadal. In fact, WFIRST turned out to be a shotgun marriage of two science programs that needed something very similar. So they basically invented a new mission on the fly and said, this is what we're going to have, and they didn't even recommend a backup. And WFIRST started to get really expensive when the National Reconnaissance Organization presented us with a telescope that was too big, which meant that all the cost just went up. And WFIRST has struggled. And right now, in fact, it's not even included in the administration's budget, but it's very likely that Congress will put it back in because they do not want to not do the highest priority science that is identified by the decadal. Okay, so NASA didn't want this to happen again. NASA says we've got to go into the decadal much better prepared than we have been in the past. So in 2013, they commissioned a roadmap study for a 30-year vision for space astrophysics. So what do we have right now? What are we going to need next? And what are we going to need in long term? So the future missions, then the intermediate time, there were 3 of them that were identified. And we identify these, all our telescopes by function first. And then they get names later. So the one I'm going to talk about today is the Large Ultraviolet Optical Infrared Surveyor, LUVOIR. There were 2 other missions that were also under study. The Far Infrared Surveyor, whose name has now been changed to the Origin Space Telescope, and the X-ray Surveyor, whose name has just been changed to Lynx, the animal that can see well in the dark. The LUVOIR is, the easiest way to characterize it is it's really the natural successor to Hubble, but it's much larger. It will have between 100 and 1,000 times the sensitivity of Hubble. So once NASA had these mission concepts, and they were very rough concepts, just sort of, here's some cool science that you can do with these kinds of telescopes. Then they wanted a detailed study. So in 2016, the NASA Astrophysics Division commissioned 4 what they call Science and Technology Definition Teams, STDTs. And they included another mission in there that came out of an exoplanet study called the Habitable Exoplanet Observatory, or HABEX. So there are 4 STDTs, and their jobs are to identify the compelling science for these missions, identify what the technical challenges that have to be met in order to carry out that science, and then identify the technical solutions. And finally have to demonstrate that the high-level goals can be accomplished with the telescopes as designed. So we're not doing optimal telescope designs now, we're doing proof of concept. We show that a solution exists, that there are engineering solutions to every problem that we can imagine. So I'll just tell you a little bit about our STDT. Our STDT is co-chaired by me and my counterpart in exoplanets, Deborah Fisher, who's a professor at Yale. We have 26 members that are drawn from the astronomical community. About half are at NASA centers or Space Telescope Science Institute, and the rest are at universities. So I mentioned that we've wanted a successor to Hubble for a long, long time. Basically, we started thinking about it in 1992. And the thing that we have been looking for is, what's the killer app? What's the thing that says, oh my God, we've got to have this telescope? Because we could do, with a larger telescope, one larger than Hubble, we would do great science. We'd do lots of great science. But what is the thing that's going to be so compelling that people will say, all right, I'm willing to pay for this. This is cool. So we have to ask an important question, and we finally have a suitable one. And is there life elsewhere in the universe? I mean, this is the most compelling scientific question ever asked. And if LUVOIR can provide a meaningful answer to this question, it will change how human beings think about themselves. The Associate Administrator for Science at NASA, Thomas Zurbuchen, calls these civilization-changing missions. And I think that's a good description. So this is a big question. We'll do lots of important astrophysics, but the thing that I think is going to be compelling, where many of NASA's stakeholders will be interested, and by NASA's stakeholders, I mean the general public, I mean the federal government, I mean universities, everybody. The aerospace companies, everybody. So this is right now the most very compelling question is, where does life come from? How is it generated? Is it the same everywhere? Is there only one solution to life, or are there many? So we start with trying to look for life that will be somehow familiar to us. In other words, we're going to look for beings that reside on planets. In fact, we're going to look for planets that might be like our own. An important smaller mission. Now, this was not a flagship mission. This was a smaller mission that was carried out relatively recently. There's a space telescope called Kepler. And Kepler searched for transiting exoplanets. And what that means is, if you look at the image down in the lower left, you can detect a slight drop in the brightness of a star as a small planet passes across its face. So you can only see such systems when they're edge on. You don't see them when they're face on and the planet is going around the star. It never eclipses it. But this is one way of finding them. And you can account for all the statistical biases that you have by looking only at edge-on systems. And you could pretty much then generalize what things will look like if you could see them at any particular inclination. So Kepler discovered thousands of planets around other stars. And the extraordinary thing that we learned is that based on the Kepler survey, we now know that at least 1 in every 6 stars has at least one Earth-sized planet orbiting it. So Kepler was designed to look at a very small piece of sky, only a quarter of a degree across. A quarter of a percent of the sky. And it looked out to a depth of about 3,000 light years. So it's looking in a cone, basically. Very small sample. But that's where you get your statistics. And the statistics improved dramatically as time went by and as we learned to use the Kepler data in a more clever way. So we have good statistics now on all the planets, but most of these are just too far away for us to study in any detail. So we know now of well over 4,000 exoplanets, 4,000 planets. I mean, this is amazing to me. I mean, when I was a kid, we thought there were 9 planets, and then it became 8, and now we're up to 4,000. Okay, the next step is another small mission, the Transiting Exoplanet Survey Satellite called TESS, which was launched just about a year ago. And TESS has a different mission. TESS is looking at nearby stars, those only up to a distance of about 200 light years. But it's looking at all the stars. So now that we know something about statistics, now we're going to try to find very specific examples that we can study in detail. So the James Webb Space Telescope will play a key role in the search for potentially habitable worlds. And the way the Webb telescope will work is it'll look at some of these transiting planets and see how the light is changed, altered, as it passes through the planet's atmosphere. So we'll be able to do, this is called transit spectroscopy, and Webb will be able to do this. Webb will not be able, however, to individually image the individual planets. That's something where we need something like LUVOIR. So JWST will determine the composition of the atmospheres of basically a handful of planets that are orbiting nearby stars and that are much smaller than the sun. So what we want to look for is the signatures of life encoded in a planet spectrum. This is basically we've got wavelength or color of light on the long axis and the x-axis, and the vertical axis we have the intensity that one would observe. This is the kind of thing that you'll be able to see with James Webb Space Telescope. It works mainly in the infrared, so these are all wavelengths then that are too far to the red to detect with our own eyes. However, there's a lot of the interesting information is at shorter wavelengths, in particular things like ozone, for example, oxygen. You see some water vapor in the infrared, but you also detect water vapor in the optical. So if we want to get a spectrum like that, though, we can't do transit spectroscopy. We have to observe the planet directly. So Kepler or TESS are unable to do that. So what we have to do is we have to have a telescope that's so powerful that it can get a spectrum of a planet that is billions of times fainter than the star next to it. So you've got two problems then. It's close to a really bright object. We have to somehow suppress the light from that object if we want to look at the planet itself. So this is not an easy thing to do. If you look at an exoplanet system, an exoplanetary system, you see that there's a glare from the star. A lot of this is actually due to diffraction. And what you need to do is get rid of the glare of the star. You need to suppress it by factors of 10 billion in order to see the individual planets. So the planets are there, and if we could suppress the starlight, oh, I lost it. Yes, if we could we would be able to see these individual planets and obtain spectra of them and determine what the chemical composition of their atmospheres is. Now, the way you can do this, there are a couple different technologies that you could use, and the one that we're favoring right now, because it doesn't require a separate satellite, is something called a coronagraph. A coronagraph historically has been used to block out the very brightest part of the sun so that you could see the faint outer envelope, which is called the corona, or crown, Latin word. And this is a very simple one on the SOHO satellite that is looking at the corona of the sun. And you can see the various phenomena that you can detect once you suppress the bright light of the sun. The little circle in the center shows you how big the sun actually is. But you can see material streaming out as a coronal mass ejection. And also on the top, interesting, you can see a comet. Okay, so that's fine. Just an opaque disk is fine if you don't need a lot of contrast. But if you really need high contrast, you need to block out not just the main image of the star, but the diffracted light as well. So if you're looking at the diffracted light, this then starts to get complicated. You start to wind up with a coronagraph that has a series of masks and stops in it that will suppress the scattered light as well. So the goal is that we want to be able to suppress the starlight by a factor of 10 billion. And that would mean that the total light from the star would be about equal to the light that you would see from an Earth-like planet next to it. The state of the art right now is that we can get a contrast of about 500 million. So really, we got this last factor of 20 that we're still working on. We got to be able to suppress it by another factor of 20. But I think that's pretty good progress, seeing that people really started working in earnest on this only within the last decade. So this gives you an idea of what, this is simulated data that shows you what our solar system would look like from 30 light years away, which is coincidentally about the distance of the TRAPPIST-1 system. Although this is clearly a view that's taken from above the ecliptic, above the plane of the planetary orbits. TRAPPIST-1 is actually close to the planet. We see our system edge on. Okay. The other thing that we have to look at is where is the planet relative to the star? And as a first guess of where we might find habitable planets, we'd say, well, it's got to be somewhere where you can have liquid water. So if it's too close to the star, the water is going to be in the form of steam. And if it's too far away, it's going to be too cold, and it's going to be in the form of ice. So you want to be somewhere in between where the water can be in liquid form. Now, there may be other places that you would look. For example, Jupiter in our own solar system is way out beyond this habitable zone. It's really cold out there. But it has one of its moons is ice covered, and underneath that ice there seems to be a liquid water ocean. So there could be, and basically that's heated by tidal stresses. So there may be other places to look, but we're going to start with the places that seem obvious to us. We'll start looking at the habitable zone. Okay, so when you're looking at such faint objects, it takes a long time to collect enough light to make sure that you really clearly see the signatures that you're looking for. So even with a 15-meter space telescope, it will still take a few days to get a spectrum of an Earth-like exoplanet that's relatively nearby. So this is why we want larger telescopes. The larger the telescope, the fainter this exoplanets we can detect. So we're going to take a look at how far we could see to various distances. And I'm sorry, I apologize for this being in parsecs, but just think of 10 parsecs is 30 light years. So we go to 20 and 30 and 40. And what we want to do is consider the chance of detecting an Earth twin if it was present around nearby stars. Could we do this? So it's a function of telescope aperture. We will get a certain number of candidate exo-Earths. So when we have a telescope aperture that's 4 meters, remember Hubble is 2.4, we can expect that we can find about 6 candidate exo-Earths based on the statistics that we know now. Those are the candidates. Remember, before we can tell if they're habitable, we have to actually observe them with LUVOIR. All we know right now is that these are rocky planets that are in the habitable zone. When we go to an 8-meter telescope, we have about 25 candidates that we can look at. With a 16-meter telescope, we're up to 100 candidates. So how big a telescope do you want to build then? And the question really comes down to a simple question: do you feel lucky? If you feel lucky, you can build a smaller telescope. But if you really want to put interesting limits on things, you want a big telescope. What does it mean if you can look at 6 candidates and you don't find a habitable planet? That doesn't statistically mean much. On the other hand, when you start looking at 100 or so, then you can start making meaningful statements. And LUVOIR is specifically designing its exoplanet program so that if it makes no detections of habitable planets, then we will be able to say with 95% confidence that there is not a habitable planet, there is not an exo-Earth in the solar neighborhood. Okay, so what we have here, a little graphic that shows you the number of rocky planets that you can find given a telescope of the aperture that's increasing down here. And this was done completely at random, and you can see that we have to get up into the 8-meter range before we find one that is potentially habitable, if they turn out to be rare, if they're only 10% of rocky planets. And then by the time we get up to sort of 11 meters or so, now we're getting a sample. We have a sample that we can compare the properties of these. And again, if we don't find any, it's statistically meaningful. It means we're it. Okay, one of the first things I said, build the biggest space telescope that you can get into space or that you can afford. And with Hubble, that was the biggest telescope you could get in the space shuttle. With James Webb, it was the largest one you could fold up inside an Ariane 5. And what do we want to do to get bigger ones? We're going to have to go to bigger launch vehicles. So if we look at the kinds of launch vehicles that have been available in the past and that we expect to have available in the future, this is sort of the big 5, where you can see the Saturn V, which is what it took to get to the moon. We couldn't build that again if we had to. No one knows. No, the plans are all gone. There are 3 unused ones sitting around, but they're museum pieces. But that was a pretty fantastic rocket. What NASA has been looking at recently is something called a Space Launch System. And there's 2 versions of it. The SLS Block 1, which you see right in the middle, that's designed to take a crew up into orbit and take them as far as the moon. The SLS Block 2 is a cargo vessel, and this was the thing that was going to make it possible to go to Mars. So whether or not we're going to do that, I'm not sure, but that's the heaviest lift capability that we have. Now, there are also private enterprises that are working on launch vehicles, notably the Falcon Heavy that you see on the far left. So what we were told to do, our instructions as the STDT were to be optimistic and assume that there was going to be an SLS, and there was going to be an SLS Block 2. So we made 2 versions of LUVOIR. We're studying 2 different apertures because we don't know if the SLS Block 2 is ever going to be there, but we're pretty sure the Block 1 will be there. So the Block 2, we can fit a 15-meter telescope in, and the Block 1, we can fit an 8-meter telescope in. So we'll study both of these apertures. Now you can see what they look like. Again, these are segmented telescopes, like the James Webb Space Telescope, and you see how much larger these are compared to the Hubble Space Telescope in particular. Just a little visual here for comparison. Here's the Hubble Space Telescope. That's good fun, but we will never have LUVOIR that close to the Earth. LUVOIR is going to be in deep space, and we'll get to that just in a minute. So again, it will, like the James Webb Space Telescope, it will have wings that will need to be folded up. Now, instead of 1 wing on each side, it will have 2 wings on each side. This is the SLS Block 2 fairing. So I'm going to show you the architecture A, which is our 15-meter, the one we'd really like. And it will deploy. Again, what you see, the first thing out are the solar panels for power. And the sequence is actually wrong on this because you have the secondary mirror and the primary deploying before the sunshade deploys. And then the central light baffle keeps stray light from going into the instruments. But the sun shield on this is very large. It's much larger than the infield of a professional baseball park. The instruments are designed to be removable. You can see them underneath the primary mirror. You can open it up and you can slide them out and repair them or replace them. And there's room for 4 scientific instruments in this one. The telescope will be completely articulated. So unlike the James Webb Space Telescope, which can only observe basically a ring around the sky, which changes, of course, as it moves through space, what we call the field of regard, which is how much sky can you look at any given time, will be very, very large. We'll be able to observe within about 45 degrees of the sun, which means that the sunshade has to be extremely large. Yes, I've got another animation here, and I want to turn the voice off on this because this is actually, we'll talk about James Webb. All right, the orbit that it will be in is called a Lagrange point. There are 5 Lagrange points. You see them here. These are places that are quasi-stable in the Earth-Sun system. The one that you see the telescope orbiting around is called Lagrange point 2. And it has the virtue that it's about 1 million miles away from the Earth. It's beyond the moon. All the bright things in the sky, meaning the sun, the Earth, and the moon, are all blocked by the sun shield. And the great thing about this is that these Lagrange points, it co-revolves with the Earth. If you're at a different point, if you're at a different point than this, as you go farther and farther out, it will trail behind. It will fall behind because the orbital speed is lower. But the Lagrange points are tricky little points that if you can sit at them, you'll get carried along at the same rate that the Earth is. So lots of other advantages too. It's very dark there and it's very cold. And the dark and cold part is important because they can keep the telescope at a constant temperature, which is what you need to do for stability. If you're going to look at a little exoplanet next to a bright star, you have to be able to point to extremely high accuracy, and you have to be able to hold your position to about the diameter of an atom. Okay, yeah, very stringent requirement, but if you are in a calm part of space, you can do this. Okay, let's compare the orbits. We've got the Sun-Earth Lagrange point 2. Compare it to low Earth orbit, where Hubble is, for example. So the advantage of being at L2 is you are in deep space. There is no atmosphere to worry about. But even at Hubble's altitude of 600 kilometers, there still is a very thin atmosphere, and there's drag, and it's slowly bringing Hubble back down into a lower orbit, and eventually the orbit will decay sufficiently that it will crash back to Earth, hopefully someplace that we can pre-select. The nice advantage then again about L2, as I mentioned this already, you have constant illumination, so you can keep the temperature of the telescope controlled. Now, in the case of James Webb Space Telescope, they're going to passively cool it to 40 degrees Kelvin. We don't want to be that cold. In fact, because this is an optical telescope, one of our major considerations really is that we don't want anything condensing on it. So we want to actually heat the telescope. LUVOIR will use half its power budget to stay warm, to stay at about 265 Kelvin, to keep water from condensing on it. Another problem with Hubble Space Telescope, is it's orbiting once every 90 minutes, which means that it spends 45 minutes in the sunlight and then 45 minutes in the dark. So that thermally cycles the telescope at a pretty high rate. And one of the things that you can't achieve with Hubble is extreme stability because of those temperature variations. As I mentioned before, you can observe more than half the sky at any given time from L2. But with Hubble Space Telescope, you can observe only half of the sky, and you get it for 45 minutes at a time. Now, some of the disadvantages are, because L2 is so far away, for a given launch vehicle, you can get less mass to orbit than you can if you're in low Earth orbit. And another consideration is that we're in low Earth orbit, servicing a telescope is practical. We've done that 5 times with Hubble. On the other hand, it becomes very difficult when you get out to L2. Because if you use a minimum amount of energy to get out to L2, it takes you 60 days to get there. And we don't have anything that certainly that astronauts could survive in for that amount of time. Robots possibly, but then the robots have to be extremely clever because the light travel time to L2 and back is 10 seconds. So you have 10 seconds latency between you tell the robot to do something and you find out if it did it. All right. I've emphasized exoplanets, but really, LUVOIR is about the study of life in the universe, and that goes back to very early universe. This is an example of what the early structure in the universe looked like. It was just gas, and out of these gas webs, you formed galaxies and stars and ultimately planets. And all of these phases of evolution of the universe will be observable with LUVOIR. Just to give you an idea of what kinds of things you can do. I'm going to look at a very distant galaxy, 2 very distant galaxies. One that is made up of about 1 billion times the mass of the Sun, another made up with about 1 million times. This is what you would see of those 2 galaxies at a very large distance with Hubble, which is 2.4 meter telescope. With a 4 meter telescope, you start to see more, but when you get up to 8 and 15, you start to see the individual structures. And the reason that this is so important, these are actual simulations done on a computer of how galaxies should form. And they're messy affairs. You see that there are all kinds of streams, and there are clearly indications of mergers that have occurred, that small galaxies come together to form larger galaxies. But this is a model, and we have to observationally confirm it before we can establish that we know something. We can also observe objects in the solar system. This is a picture of Jupiter taken with a Juno probe. And this is when Juno is very close to Jupiter. At basically once a year with LUVOIR, we can get images that will exceed the quality of this image that you see here. So you can start to look at evolution of fine phenomena, look at weather on Jupiter, not just climate. Around Jupiter, one of its moons I mentioned before is Europa. Europa is the frozen ice ball that seems to have a liquid water ocean underneath the surface. We see jets coming off of these, and if we had the kind of resolution that you could get with a 15-meter LUVOIR, this is the level of detail that you could see compared to what you can see with a Hubble Space Telescope over on the left. Pluto. Pluto is very small and very far away. And this is basically what it looks like with a Hubble Space Telescope. With a 15-meter LUVOIR, you can start to see some of the detail that you were able to see with the New Horizons, which passed by a few years ago and took these very detailed images of only one side. So the reason that this is actually interesting science is because Pluto has a very eccentric orbit. And sometimes it's much closer to the sun than other times. And you expect seasons. And we know that there are seasons because Pluto has a relatively bright surface. And that means the methane ice, which is exposed to solar ultraviolet radiation, hasn't been there long enough to turn black. So the technological challenges that we have to meet for something like LUVOIR. The first thing, which turned out to be not that hard, we took care of it early, is that for a long time it was felt that coronagraphy and ultraviolet observations were incompatible for the very simple reason that the ultraviolet reflective coatings were too rough. They're now smooth enough that we can use those with the telescope mirror and it will not hurt the coronagraphy. Deployment of large segmented telescopes. Well, that's one that we're trying with JWST. And we will know within a couple of years how successful that is going to be. We need a heavy lift launch vehicle with a large fairing. And it looks like they are coming up with an 8-meter LUVOIR will not be hard. There will be a number of commercial vehicles that can do that. For the 15-meter LUVOIR, it will require the SLS block too. And then the really tricky part is we need to do ultra-high contrast observations with a segmented telescope. The diffraction pattern for a segmented telescope is more complicated than for a single monolith. So we have to figure out ways to do that. And again, as I said earlier, we're within a factor of about 20 doing that. So the important takeaway from this is that the next generation of space telescopes, it's going to be larger and it's going to take longer to develop than the predecessors. Now that means it's incumbent upon us to do things differently. We have to break, we call break the cost curve. You know, there's a plot that you can make of telescope aperture versus cost, and it's not pretty. So we have to break the cost curve by innovation, by figuring out more clever ways to build large structures, but using the technical heritage that has already been developed, using the things that we developed for JWST and for Hubble Space Telescope. And if we're going to spend a lot of money on these telescopes, they can't be expendable telescopes. You can't build a telescope that's $10 billion and then after a decade just walk away from it. That's just irresponsible. So we have to figure out how to service these telescopes and how to upgrade them, how to put in new generations of instruments like we have been able to do with Hubble Space Telescope. And we also have to encompass a broad range of science. We cannot do narrow science based on very expensive individual telescopes. So in summary, LUVOIR has multiple primary science goals. 3 of them in particular are habitable exoplanets and biosignatures. A broad range of general astrophysics, looking at stars and galaxies, and also looking locally, doing solar system studies. We can blend all of these into a single powerful mission. And LUVOIR will be able to do imaging and spectroscopic exoplanet survey, enabling a statistically meaningful constraint on the occurrence of habitable and possibly even inhabited planets. LUVOIR will provide factors of 10 to 2,000 increased science grasp over HST and JWST for astrophysics, in particular for things we're looking at point sources against a bright background. And I will stop there and be happy to take any questions that you have.